Hello everyone, welcome back. I'm your friend in Saxo. Today we're going to learn the
Congruence.
Congruence. Right, let's get into it, even though I don't know what that means.
We're told Kassan was curious if triangle ABC and triangle GFE were congruent. So he tried to map one figure onto the other using a rotation. So let's see, this is triangle ABC, and it looks like at first he rotates triangle ABC about point C to get it right over here. So that's what they're depicting in this diagram. And then they say Kassan concluded it is not possible to map triangle ABC onto triangle GFE using a sequence of rigid transformations. So the triangles are not congruent. So what I want you to do is pause this video and think about, is Kassan correct that they are not congruent because you cannot map ABC, triangle ABC onto triangle GFE with rigid transformation? All right. So the way I think about it, he was able to do the rotation that got us right over here. So it was rotation about point C. And so this point right over here, let me make sure I get this right. This would have become B prime, and then this is A prime, and then C is mapped to itself. So C is equal to C prime. But he's not done. There's another rigid transformation he could do, and that would be a reflection about the line FG. So if he reflects about the line FG, then this point is going to be mapped to point E, just like that. And then if you did that, you would see that there is a series of rigid transformations that maps triangle ABC onto triangle GFE. So Kassan is not correct. He missed one more transformation he could have done, which is a reflection.
Shit, I guess the word congruent here means the two objects, they are exactly the same, or they have the same shape.
We are told Brenda was able to map circle M onto circle N using a translation and a dilation. All right, so this is circle M right over here. Here's the center of it. And this is circle M, this circle right over here. And so it looks like at first she translates it. So the center goes from this point to this point here. And so after the translation, we have the circle right over here. And then she dilates it. And the center of dilation looks like it is point N. And so she dilates it with some type of a scale factor in order to map it exactly onto N. All right, so that all seems right. Now, Brenda concluded, I was able to map circle M onto circle N using a sequence of rigid transformations. So the figures are congruent. So is she correct? Pause that video, or pause this video, and think about that. All right, now let's work on this together. So she was able to map circle M onto circle N using a sequence of transformations. She did a translation and then a dilation. Those are all transformations. But they are not all rigid transformations. I'll put a question mark right over there. A translation is a rigid transformation. Remember, rigid transformations are ones that preserve distances, preserve angle measures, preserve lengths, while a dilation is not a rigid transformation. As you can see very clearly, it is not preserving lengths. It is not, for example, preserving the radius of the circle. In order for two figures to be congruent, the mapping has to be only with rigid transformations. So because she used a dilation, in fact, you have to use a dilation if you want to be able to map M onto N because they have different radii, well, then she's not correct. These are not congruent figures. She cannot make this conclusion.
Okay, I guess I already mastered those stuffs. Let's say another one, triangle congruence from transformation. What is that?
What we're going to do in this video is see that if we have two different triangles where the corresponding sides have the same measure, so this orange side has the same length as this orange side, this blue side has the same length as this blue side, this gray side has the same length as this gray side, then we can deduce that these two triangles are congruent to each other based on the rigid transformation definition of congruence. And to show that, we just have to show that there's always a series of rigid transformations that maps triangle ABC onto triangle EDF. So how do we do that? Well, first of all, in other videos, we showed that if we have two line segments that have the same measure, they are congruent. You can map one onto the other using rigid transformations. So let's do a series of rigid transformations that maps AB onto ED. And you can imagine how to do that. You would translate point A, you would translate this entire left triangle so that point A coincides with point E, and then side AB would be moving in, this would be on this direction over here, and then you would rotate around this point right over here. You could call that A prime, so this is going to be equal to A prime. You rotate around that so that side AB coincides with side ED, and we've talked about that in other videos. So at that point, D would be equal to B prime, the point to which B is mapped. But the question is, where is C? If we can show that for sure C is either at point F or with another rigid transformation we can get C to point F, then we would have completed our proof. We would have been able to show that with a series of rigid transformations you can go from this triangle, or you can map this triangle onto that triangle. And to think about where point C is, this is where this compass is going to prove useful. We know that point C is exactly this far away from point A. I will measure that with my compass, so I could do it this way as well. Point C is exactly that far from point A. And so that means that point C needs to be someplace on this curve right over here, on this arc that I'm doing. These are some of the points that are exactly that far away. I could do a complete circle, but you see where this is going. So point C, I guess we could say C prime, or C will be mapped to some point on that circle, if you take it from A's perspective, because that's how far C is from A. But then we also know that C is this far from B. So let me adjust my compass again. C is that far from B. And so if B is mapped to this point, this is where B prime is, then C prime, where C is mapped, is going to be someplace along this curve. And so you could view those two curves as constraints, so we know that C prime has to sit on both of these curves. So it's either going to sit right over here where F is, and so if my rigid transformation got us to a point where C sits exactly where F is, well then our proof is complete. We've come up with a rigid transformation. Now another possibility is when we do that transformation, C prime ends up right over here. So what could we then do to continue to transform rigidly so that C prime ends up with F? Remember, the other 2 points have already coincided with E and D, so we just have to get C prime to coincide with F. Well, one way to think about it is, if we think about it, point E is equidistant to C prime and F. We see this is going to be equal to, we could put 3 hashtags there, because once again, that defined the radius of this arc. And we know that point C prime in this case, is the same distance from D as F is. And so one way to think about it, imagine a line between F and, let me get my straight edge here so it looks a little bit neater. Imagine a line that connects F and this C prime. And once again, we're in the case where C prime immediately didn't go to F, where C prime ended up being on this side, so to speak. And you can see that point E, because it is equidistant to C prime and F, it must sit on the perpendicular bisector of the segment FC. Same thing about point D, or B prime. This must be the perpendicular bisector, because this point is equidistant to F as it is to C prime. This point is equidistant to F as it is to C prime. The set of points whose distance is equal to F and C prime, they will form the perpendicular bisector of FC. So we know that this orange line is a perpendicular bisector of FC. Why is that helpful? Well, that tells us is if when we do that first transformation to make AB coincide with EF, if C prime doesn't end up here and it ends up there, we just have to do one more transformation. We just have to do a reflection about ED, or about A prime, B prime, however you want to view it, about this orange line, and then C will coincide with F, because orange is a perpendicular bisector, so I could do something like this. This length is the same as this length, And since it's perpendicular bisector, when you do the reflection, C prime will then coincide with F. And a reflection is a rigid transformation, so we would be all good.
I don't know the point for this video. Congruent triangles.
We now know that if we have two triangles and all of their corresponding sides are the same, so by side, 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 so if the corresponding sides, all three of the corresponding sides have the same length, we know that those triangles are congruent. What I want to do in this video is explore if there are other properties that we can find between the triangles that can help us feel pretty good that those two triangles would be congruent. So side, side, side works. What about angle, angle, angle? So let me do that over here. What about angle, angle, angle? So what I'm saying is if, let's say I have a triangle like this, like I have a triangle like that, and I have a triangle like this, and if we know that this angle is congruent to that angle, if this angle is congruent to that angle, which means that their measures are equal, and that angle is congruent to that angle, can we say that these are two congruent triangles? And at first case, it looks like maybe it is, at least the way I drew it here. But when you think about it, you can have the exact same corresponding angles having the same measure or being congruent, but you can actually scale one of these triangles up and down and still have that property. For example, if I had this triangle right over here, it looks similar, and I'm using that in just the everyday language size. It has the same shape as these triangles right over here, and it has the same angles. That angle is congruent to that angle. This angle down here is congruent to this angle over here. And this angle over here is congruent to this angle over here. So all of the angles in all three of these triangles are the same. The corresponding angles have the same measure. But clearly this triangle right over here is not the same. It is not congruent to the other two. The sides have a very different length. This side is much shorter than this side right over here. This side is much shorter than that side over there. And this side is much shorter over here. So with just angle, 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 you cannot say that a triangle has the same size and shape. It does have the same shape, but not the same size. So this does not imply congruency.
Alright, so through this video, we at least know one thing, which is in the foreign people or in the United States people or whatever, in the English-speaking nation, they will not consider the shape as a standard for the two objects to be equal. They would consider the word called size. Okay, only if they have the same shape and the same size, they would consider the two objects are equal. That was different. So if two objects have the same shape, it may mean that they are both, for example, they are both triangle but with different size, or they are both square but with different size, something like that. But here, as I could imagine, so how can you say that two triangles, they are the same, or in this case, they call it they are congruent? How can you say that? Well, according to my experience, there has basically three different cases. The first case is the three sides of them have the same length. That's the first case. They call it SSS, but I don't want to call that. And the second case is that they have a same angle, while they also have two sides which have the same length. In this case, since this angle and two sides are unknown, then this line must be the same. And also there has another case. Let me say the third case is when you know two angles and a side length, when three of them are equal, then since we know this angle, this side, so the two lines will eventually cross always at the same point. So for this case, they are the two triangles. They are also identical or congruence.
So angle, angle, angle does not imply congruency. What it does imply, and we haven't talked about this yet, is that these are similar triangles. So angle, angle, angle implies similar. So let me write it over here. It implies similar triangles. And similar, you probably are used to the word in just everyday language, but similar has a very specific meaning in geometry. And similar things have the same shape, but not necessarily the same size. So anything that is congruent, because it has the same size and shape, is also similar, but not everything that is similar is also congruent. So for example, this triangle is similar to all of these triangles are similar to each other, but they aren't all congruent. These two are congruent if their sides are the same. I didn't make that assumption, but if we know that their sides are the same, then we can say that they're congruent. But neither of these are congruent to this one right over here, because this is clearly much larger. It has the same shape, but a different size. So we can't have an AAA postulate or an AAA axiom to get to congruency. What about side, angle, side? So let's try this out. Side, angle, side. So let's start off with one triangle right over here. So let's start off with a triangle that looks like this. I have my blue side, I have my pink side, and I have my magenta side. And let's say that I have another triangle that has this blue side. It has the same length as that blue side. So let me draw it like that. It has the same length as that blue side. So that length and that length are going to be the same. It has a congruent angle right after that. So this angle and the next angle for this triangle are going to have the same measure, or they're going to be congruent. And then the next side is going to have the same length as this one over here. So that's going to be the same length as this over here. So it's going to be the same length. And we don't know, and because we only know that they have that two of the corresponding sides have the same length, and the angle between them, and this is important, the angle between the two corresponding sides also have the same measure, we can do anything we want with this last side on this one. We can essentially, it's going to have to start right over here. You could start from this point, and we can pivot it to form any triangle we want. But we can see the only way we can form a triangle is if we bring this side all the way over here and close this right over there. And so we can see just logically that if for two triangles, they have one side that has the length the same, the next side has the length the same, and the angle in between them. So this angle, let me do that in the same color. This angle in between them, this is the angle. This A is this angle and that angle. It's the angle in between them. This first side is in blue, and this second side right over here is in pink. And well, it's already written in pink. So we can see that if two sides are the same, have the same length, two corresponding sides have the same length, and the corresponding angle between them, they have to be congruent. There's no other place to put this third side. So SAS, and sometimes it's once again called a postulate, an axiom, or if it's kind of proven, sometimes it's called a theorem. This does imply that the two triangles are congruent. So we will give ourselves this tool in our toolkit. We had the Sss postulate.
You know what? Back to my school, the Chinese school, they often say some rules like this, SAS or SSS or A, kind of things like that. They just want to tell you the rules. They use some sentences to describe that rules. But the problem is people, some people like me do not understand what you are saying about the rules. The truly important stuff is to know what that rules does, or how can you how can you prove that rule is correct. For example, for this one, SAS, if I only tell you this word, how can you know what that means? But when you look at the two graphs, you would generally know that when you get two sides equal, have the same length, then you have the corresponding angle have the same measure. Then the third side, you have nowhere else to put the third side to form a triangle. So it has to be this line will always be at a certain place. So that's why this rule works. That's why they are identically equal. So sometimes you have to see the multiple examples to conclude the rule. But for those Chinese school, they are likely try to tell you the rule, but without tell you the examples, or they just provide one example, which is definitely not enough. So in our real life, we do not know the rule at the first, but instead we will see a lot of examples. But whether can you conclude a rule, that's a measure for your intelligence. I hope you understand what I am saying.
Now we have the Sas postulate. Two sides are equal and the angle in between them for two triangles, corresponding sides and angles, then we can say that it is definitely these are congruent triangles. Now what about, and I'm just going to try to go through all of the different combinations here. What if I have angle, side, angle? So let me try that. So what happens if I have angle, side, angle? So let's go back to this one right over here. So actually, let me just redraw a new one for each of these cases. So angle, side, angle. So I'll draw a triangle here. So I have this triangle. So this would be maybe the side. That would be the side. So let me draw the whole triangle actually first. So I have this triangle. Let me draw one side over here. And then let me draw one side over there. And that this angle right over here, I'll do it in orange. And this angle over here, I will do it in yellow. So if I have another triangle that has one side having equal measure, so I'll use it as this blue side right over here. So it has one side that has equal measure, and the two angles on either side of that side, or at either end of that side, are the same, will this triangle necessarily be congruent? And we're just going to try to reason it out. These aren't formal proofs. We're really just trying to set up what are reasonable postulates or what are reasonable assumptions we can have as we kind of, in our toolkit as we try to prove other things. So that angle, let's call it that angle right over there, is going to be, they're going to have the same measure in this triangle. And this angle right over here in yellow is going to have the same measure on this triangle right over here. So regardless, so I'm not in any way constraining the sides over here. So this side right over here could have any length. It could have any length, but it has to form this angle with it. So it could have any length, and it can just go as far as it wants to go. In no way have we constrained what the length of that is. And actually, let me mark this off too. So this is the same as this. So that side can be anything. We haven't constrained it at all. And once again, this side could be anything. We haven't constrained it at all, but we know it has to go at this angle. So it has to go at that angle. Well, once again, there's only one triangle that can be formed this way. We can say all day that this length could be as long as we want or as short as we want, and this one could be as long as we want or as short as we want. But the only way that they can actually touch each other and form a triangle and have these two angles is if they are the exact same length as these two sides right over here. So this side will actually have to be the same as that side, and this would have to be the same as that side. Once again, this isn't a proof. I'd call it more of a reasoning through it or an investigation, really just to establish what are reasonable baselines or axioms or assumptions or postulates that we can have. So for my purposes, I think ASA does show us that two triangles are congruent. Now let's try another one. Let's try angle, angle, side. Let's try angle, angle, side. And in some geometry classes, and maybe if you have to go through an exam quickly, you might memorize, okay, side, side, side implies congruency, and that's kind of logical. Side, angle, side implies congruency, and so on and so forth. I'm not a fan of memorizing it. It might be good for time pressure. It is good to sometimes even just go through this logic. If you're like, wait, does angle, angle, angle work? Well, no, I can find this case that breaks down angle, angle, angle. If these work, just try to verify for yourself that they make logical sense why they would imply congruency. Now let's try angle, angle, side. Let's try angle, 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 side. So once again, let's have a triangle over here. It has some side. So this one's going to be a little bit more interesting. So it has some side. That's the side right over there. And then it has two angles. And let me draw the other sides of this triangle. I'll draw one in magenta and then one in green. And there's two angles and then the side. So let's say you have this angle. You have that angle right over there. Actually, I didn't have to put a double because that's the first angle that so I have that angle, which we refer to as that first A. then we have this angle, which is that second A. So if I know that there's another triangle that has one side having the same length, so let me draw it like that. It has one side having the same length. It has one angle on that side that has the same measure. So it has a measure like that. And so this side right over here could be of any length. This side over here could be at any length. We aren't constraining what the length of that side is. But whatever the angle is on the other side of that side is going to be the same as this green angle right over here. So for example, it could be like that, and then you could have a green side go like that. It could be like that, and have the green side go like that. And if we have, so the only thing we're assuming is that this is the same length as this, and that this angle is the same measure as that angle, and that this measure is the same measure as that angle. And this magenta line can be of any length, and this green line can be of any length. We in no way have constrained that. But how can we form any triangle that is not congruent to this? Because the bottom line is this green line is going to have to touch this one right over there, and the only way it's going to touch that one right over there is if it starts right over here. It starts right over here because we're constraining this angle right over here. We're constraining that angle. And so it looks like angle side does indeed imply congruency. So that does imply congruency. So let's just do one more just to kind of try out all of the different situations. What if we have, and I'm running out of a little bit of real estate right over here at the bottom. What if we tried out side, side, angle? So once again, draw a triangle. So it has one side there. It has another side there. And then I don't have to do those hash marks just yet. So one side, then another side, and then another side. And what happens if we know that there's another triangle that has two of the sides the same and then the angle after it? So for example, it would have that side, just like that.
All right. When you look at this row, you know this side is certain. This angle is certain. This angle is certain. Then even if you can go to here, because this purple line can be infinitely long. Even if you could go to there, this line, this side will never touch this side. So if you want to form a triangle, it must be in here. So in this way, it also makes two triangle identical, which is equal.
And then it has another side, but we're not constraining the angle. We aren't constraining this angle right over here, but we're constraining the length of that side. So let me color code it. So that blue side is that first side. Then we have this magenta side right over there. So this is going to be the same length as this right over here, but let me make it at a different angle to see if I can disprove it. So let's say it looks like that. Or actually, let me make it even more interesting. Let me try to make it like that. So it's a very different angle, but now it has to have the same angle out here. It has to have that same angle out here. So it has to be roughly that angle. So it actually looks like we can draw a triangle that is not congruent, that has the same two sides being the same length, and then an angle is different. For example, this is pretty much that. I made this angle smaller than this angle. These two sides are the same. This angle is the same now, but what the byproduct of that is that this green side is going to be shorter on this triangle right over here. So you don't necessarily have congruent triangles with side-side angle. So this is not necessarily congruent. Not necessarily. Or similar. It gives us neither congruency nor similarity.
Angles in triangle sum to 108 proof. You know what? Back into the school, we will treat this as a row to memorize, but we never know why. It always sums up to 108 degree. We don't know that.
I've drawn an arbitrary triangle right over here, and I've labeled the measures of the interior angles. The measure of this angle is x, this one's y, this one is z. And what I want to prove is that the sum of the measures of the interior angles of a triangle, that x plus y plus z, is equal to 180 degrees. And the way that I'm going to do it is using our knowledge of parallel lines or transversals of parallel lines and corresponding angles. And to do that, well, I'm going to extend each of these sides of the triangle, which right now are line segments, but extend them into lines. So this side down here, if I keep going on and on forever in the same directions, then now all of a sudden I have an orange line. And what I want to do is construct another line that is parallel to the orange line that goes through this vertex of the triangle right over here. And I can always do that. I can just start from this point and go in the same direction as this line, and I will never intersect. I'm not getting any closer or further away from that line. So I'm never going to intersect. I'm never going to intersect that line. So these two lines right over here are parallel. This is parallel to that. Now I'm going to go to the other two sides of my original triangle and extend them into lines. So I'm going to extend this one into a line. So do that as neatly as I can. So I'm going to extend that into a line. And you see that this is clearly a transversal of these two parallel lines. Now, if we have a transversal here, then that means, of two parallel lines, then we must have some corresponding angles. And we see that this angle is formed when the transversal intersects the bottom orange line. Well, what's the corresponding angle when the transversal intersects this top blue line? What's the angle on the top right of the intersection? Angle on the top right of the intersection must also be x. The other thing that pops out at you is there's another vertical angle with x, another angle that must be equivalent. On the opposite side of this intersection, you have this angle right over here. These two angles are vertical, so if this has measure x, then this one must have measure x as well. Let's do the same thing with the last side of the triangle that we have not extended into a line yet. So let's do that. So if we take this one, so we just keep going, so it becomes a line. So now it becomes a transversal of the two parallel lines, just like the magenta line did. And we say, hey, look, this angle y right over here, this angle is formed from the intersection of the transversal and the bottom parallel line. What angle does it correspond to up here? Well, this is kind of on the left side of the intersection. It corresponds to this angle right over here where the green line, the green transversal intersects the blue parallel line. Well, what angle is vertical to it? Well, this angle. So this is going to have angle, or it's going to have measure y as well. So now we're really at the home stretch of our proof, because we will see that the measure, we have this angle and this angle. This has measure angle x. This has measure z. They're both adjacent angles. If we take the two outer rays that form the angle, and we think about this angle right over here, what's this measure of this white angle right over there? What's going to be x plus z, x plus z, and that angle is supplementary to this angle right over here that has measure y. So the measure of the measure of this white angle, which is x plus z, plus the measure of this magenta angle, which is y, must be equal to 180 degrees because these two angles are supplementary. So so the measure of the white angle, x plus z, plus the measure of the magenta angle, which is supplementary to the white angle, it must be equal to 180 degrees because they are supplementary. Well, we could just reorder this if we want to put it in alphabetical order, but we've just completed our proof. The measure of the interior angles of the triangle, x plus z plus y, we could write this as x plus y plus z if the lack of alphabetical order is making you uncomfortable. We could just rewrite this as x plus y plus z is equal to 180 degrees. And we are done.
All right, that was simple. I think I could also be a mathematician, like they did. I guess it's kind of simple. All right, it seems like they have a lot of different theories. For example, the midpoint theory.
So we have these two parallel lines, line segment AB and line segment CD. They are parallel, I should say they're parallel line segments. And then we have these transversals that go across them. So you have this transversal BC right over here, and you have this transversal AD. And what this diagram tells us is that the distance between A and E, this little hash mark, says that this line segment is the same distance as the distance between E and D. Or another way to think about it is that point point E is at the midpoint, or is the midpoint of line segment AD. And what I want to think about in this video is point E also the midpoint of line segment BC? So this is the question right over here. So is E the midpoint of line segment BC? And you can imagine, based on a lot of the videos we've been seeing lately, maybe it has something to do with congruent triangles. So let's see if we can set up some congruency relationship between the two obvious triangles in this diagram. We have this triangle up here on the left, and then we have this trigram down here. This one kind of looks like it's pointing up. This one looks like it's pointing down. So there's a bunch of things we know about vertical angles and angles of transversals. The most obvious one is that we have this vertical. We know that angle AEB is going to be congruent, or its measure is going to be equal to the measure of angle CED. So we know that angle AEB is going to be congruent. AEB is going to be congruent to angle DEC. Congruent to angle DEC, which really just means they have the exact same measure. And we know that because they are vertical angles. They are vertical angles. Now we know that AB and CD are parallel. So this line right over here, this is transversal. So we know, for example, and there's actually several ways that we can do this problem, but we know that this is a transversal. And there's a couple of ways to think about it right over here. So let me just continue the transversal so we get to see all of the different angles. You could say that this angle right here, angle ABE, so this is its measure right over here. You could say that it is the alternate interior angle to angle ECD, to this angle right over there. And if that didn't jump out of you, you would say that the corresponding angle to this one right over here is this angle right up here. If you were to continue this line off a little bit, these are the corresponding angles, and then this one is vertical. But either way, angle AEB, let me write this down. Angle ABE, let me be careful. Angle ABE is going to be congruent to angle, so that's ABE, is congruent to angle DCE. It's congruent to angle DCE. And we could say because it's alternate interior angles. I'll just write a little code here. So alt interior angles. And then we have an interesting relationship. We have an angle congruent to an angle, another angle congruent to an angle, and then the next side is congruent to the next side over here. So pink, green side. Pink, green side. So we can employ AAS, angle, side, and it's in the right order. So now we know that triangle, we have to make sure that we get the letters right here, that we have the right corresponding vertices. We can say that triangle AEB, actually let me start with the angle just to make it interesting. Angle BEA, so we're starting with the magenta angle, going to the green angle, and then going to the one that we haven't labeled. So angle BEA, we can say is congruent to angle. We start with the magenta vertices, C, go to the center, E, and then go to the unlabeled one, D. And we know this because of angle, side, and all of and they correspond to each other. Magenta, green side, they're all congruent. So this is from AAS. And then if we know that they are congruent, then that means corresponding sides are congruent. So then we know that this side, so we know these two triangles are congruent, so that means that their corresponding sides are congruent. So then we know that length of BE, the length of that segment BE is going to be equal. And that's the segment that's between the magenta and the green angles. The corresponding side is side CE, between the magenta and the green angles, is equal to CE. And this just comes out of the previous statement. If we number them, that's 1.
All right. So when you look at those segments, you have to know one thing, which is this symbol here just means the equals operation, no? Or it means the equal relationship. between two objects. But it's specified to the angle. But with some general variable or the length kind of stuff, we could just use this symbol, the equal symbol, to represent the equality of two stuffs. Yeah, but the real thing I just want to point out is that, in traditional classroom or in traditional class, the teacher would always try to, speak the angle with something like this, AEB or ABE, or they speak out the triangle with some symbols like BA or CED, but they will never point out the corresponding object in the blackboard. They would never do that, but they just speak out those stupid sequence of characters. When they speak up that, they do not point out what they are referring to, which can cause some problems because for most of the students, especially for those for the students who are not so good at the geometry, they will not be able to follow the teacher's thoughts that quick. But like this teacher, the Kahan, he did very good at this, because whenever he read a new variable like this, angle AB, he will point out, use his mouse, for example, the angle AEB. Then you would say it clearly, what's the angle AB? Or when he sees the triangle, he would say, for example, BA, he will use his mouse to point out the triangle BEA. Then you would clearly say what he was talking about, what kind of object he was talking about. So that was nice. That's the right way of teaching. All right, let's get into another one.
So we're told that quadrilateral ABCD is a square, which tells us that the four sides have equal length and that all the interior angles are 90 degrees. We also know that FG is a perpendicular bisector of BC. So we've already shown that it's perpendicular, that this is a 90-degree angle, but it also bisects BC. So this length is equal to that length right over there. Then they tell us that arc AC, that's a curve on top, arc AC is part of circle B. So this is a circle centered at B. So if this is the center of the circle, this is part of that circle. It's really kind of the bottom left quarter of that circle. And then given that information, they want us to find what the measure of angle BED is. So what is BED? So it's BED. So we need to figure out the measure of this angle right over here. And I encourage you to pause it and try it out. And you might imagine, well, you could pause it and try it without any hints. And now I will give you a hint if you tried it the first time and you weren't able to do it, and you should pause.
Okay, let me do this by myself. Find the let's say the measure of BED. Find the measure of BED. Well, how can you think about it? How can you solve this problem? It's kind of weird because we don't know that. All we know is that this is a right angle, and this is also a right angle. Okay, I guess I couldn't solve it because I have no thoughts about it.
Pause again after this hint, is try to draw some triangles that maybe split up this angle into a couple of different angles, and it might be a little bit easier. You might be able to use some of what we know about triangles. Now, with that said, I will try to solve it, and you should pause at any point where you think that you know exactly how to do this and try to do it yourself. So the trick here is to realize that this is a circle, and so any line that goes between B and any point on this arc is going to be equal to the radius of the circle. So AB is equal to the radius of the circle, BE is equal to the radius of the circle, and we can keep drawing other things that are equal to the radius of the circle. BC is equal to the radius of the circle. So let's think about it a little bit. if we were to draw, and a lot of trickier geometry problems really all revolve around drawing the right lines or visualizing the right triangles. And I'll do one right here that might open up a lot for you in terms of thinking about how to do this problem. So let me draw segment EC and draw that as straight as possible. I can draw a better job of that. So segment EC. Now something becomes interesting, because what is the relationship between triangle EBG and triangle ECG? Well, they both definitely share, this side right over here. They both share side EG. And then BG is equal to GC. And they both have 90-degree angles. You have a 90-degree angle here. You have a 90-degree angle there. So you see by side, angle, side, that these two triangles are going to be congruent. So we know that triangle EBG is congruent to triangle ECG. ECG, I should emphasize the C, not the E. ECG by side, angle, side congruency. By side, angle, side congruency. And that also tells us that all of the corresponding angles and sides are going to be the same. So that tells us right there that EC is equal to EB. EC is equal to EB. So we know that EB is equal to EC. And what also is equal to that length? Well, once again, this is the radius of the circle. BE is one radius of the circle going from the center to the arc. But so is BC. It is also a radius of the circle going from the center to the arc. So this is also equal to BC. So I could draw this. I'll draw the three things right here. I'm referring to the entire thing, not just one of the segments, all of BC. So what kind of a triangle is this right over here? Triangle BEC. Triangle BEC is equilateral. Equilateral, and we know that because all three sides are equal. So that tells us that all of its angles are equal. So that tells us that the measure of angle BEC, we're not done yet, but it gets us close, is 60 degrees. So the measure of angle BEC right over there is 60 degrees. So that gives us part of the problem. BEC is part of the angle BED. If we can just figure out the measure of angle CED now, if we can figure out this angle right over here, we just add that to 60 degrees, and we're done. We've figured out the entire BED. And let's think about how we can do this right over here. So there's a couple of interesting things that we already know. We know that this right over here is equal to the radius of the circle.
Okay, I guess I already figured out how to solve this kind of problem. So at the first, you know that this is the radius of the circle, and this is also the radius of the circle. So the two lines, they are the same. And we're not done yet. Let's say we have one side the scene, we have another side the scene, and we have the corresponding angle the same. So the two triangle, they are congruent. Okay, well, they are congruent. This side equal to this side. So what do they call this kind of triangle? They call it equalized. But I guess that the meaning for that is that each of the angle, they are 60 degree. Okay, since that was true, let me see what else we can get. Okay, then this angle should be 30 degree, and this angle is 90 degree. Then 90 degree minus 30 degree, that would be 60 degree for this angle. And for this angle, because it's a right angle, so for this angle it's equal to 30 degree. And again, we know that this line equal to this line. And since it's a square, so this line will also equal to the two lines. So for this case, this line equal to this line. Okay, when that was true, and if this is 30 degree, then 90 degree minus 30 degree, Oh, sorry. It should be 180 degree minus 30 degree. So this angle plus this angle equal to 150 degree. For each part, that will be 150 over 2, which is 75 degree for this part. Okay, so 75 plus 60 would be the final answer, which is 135 degree. Okay, we could verify that when we reach the end of this video.
Circle, and we also know that this length down here, this is a square. We know that this length down here is the same as this length up here, that these are the exact same length. And this is equal to the radius of the circle. We already put these 3 slashes here. BC is the same as that length, is the same as that length. And so all four sides are going to be that same length because this is a square. So let me write this down. Because it's a square, I'll just write it this way. Because it's a square, we know that CD is equal to BC, which is equal to, and we already established, which is equal to EC, which is equal to EB, which is equal to EC. But the important thing here is to realize that this and this are the same length. And the reason why that is interesting is it lets us know that this is an isosceles triangle. It's an isosceles triangle. So whatever isosceles triangle, if you have your 2 legs of it, the 2 base angles are going to be congruent. So whatever angle this green angle is, this angle is going to be as well. So if somehow we can figure out this angle right over here, we can subtract that from 180 and then divide by 2 to figure out these two because we know that they're the same. So how can we figure out this angle? Well, we know all of the angles of this thing up. We can figure out the angles of all of this larger one up here. We know this is equilateral triangle. So this over here has to be 60 degrees as well. That's 60 degrees, and that is also 60 degrees. In fact, I could write over here, which is equal to the measure of angle BCE. Measure of angle BCE. BCE. So if this is 60 degrees, we know we're dealing with a square, so this whole angle over here is a right angle. What is the measure of angle ECD? What is this angle right over here? Let me do this in a new color. This right over here is going to have to be 30 degrees. So that is going to be 30 degrees. And now we're ready to solve. Now we're ready to solve for these 2 base angles. If we call these x, and we know they have to be the same, we have x plus 30 degrees, x plus 30 degrees is going to be equal to 180 degrees. That's the sum of all of the interior angles of a triangle. So you get 2x plus 30 is equal to 180 degrees. Now you can subtract 30 from both sides, and we are left with 2x is equal to 150. Divide both sides by 2, you get x is equal to 75. So we figured out that x is equal to 75, and now we're at the home stretch. We need to figure out angle BED. Well, that's going to be angle C, so x is equal to the measure of angle CED. So BED is CED plus BEC. So the 60 degrees plus 75 degrees. So it's going to be, ready for the drum roll, this is going to be equal to 75 degrees plus 60 degrees, which is equal to 135 degrees.
So we are done. We successfully figured out the final result,
and
which is 135 degree. That was great. Okay, I guess the real important thing for you to do is to remember. Okay, the real important thing for you to remember is to recognize 2 words. The first one is called equilateral triangles. The second one is called isosceles triangle. They are 2 different things. Okay, here I'm gonna use a translator to do the job for you. And you would say that's how they call it, isolates.
Isosceles and equilateral triangles problems.
Isosceles and equilateral triangle problems.
isosceles and equilateral triangles problems.
Isosceles and equilateral triangle problems. So for the isosceles triangle, it means the two sides they are equal. And for the equilateral triangle, which means the three sides of the triangle, they are all equal. There are two different concepts for a triangle. So that's what we have learned today. And inside of this video, we have learned about the concept of congruence, which is for me are another word for describing two objects are identical, the same, both the shape and the size. Alright, so that's today's video, and I will see you guys in the next one. Bye!